Welcome. In this video, I introduce how to manually compute the standard deviation. And I'm going to preface that by saying the technology is much better and more efficient at doing this. So I mostly want to show you where this value comes from by computing it manually. But after this example, you should definitely use technology to compute these. So first, as we learned in the last module, or the last module part, measures of center can tell us a lot about data. So let's begin by computing the mean here. So this is 50 plus 57 plus 60 plus 66 plus 52. And we have 5 total values, 1, 2, 3, 4, 5. So we're going to divide this by 5. And you should end up with 285 divided by 5, which is exactly 57. So in this module, we concern ourselves with figuring out how far things away are from the middle, or so how spread out the data is. So let's begin by writing out a table. So I'm going to start with the data value of x. And you notice I'm making this table a bit long. You should do the same. And then I'm going to list these values out: 50, 57, 60, 66, and 52. Okay, so now I want to find out, or actually I want to compute the difference, or how far away each of these is individually from the middle. So I'm going to label my mean with the Greek letter mu, and here I'm going to compute x minus mu. So here I have 50 minus 57, and that equals -7. Here I have 57 minus 57, that equals 0. Here I have 60 minus 57, so that's 3. And keep going in this manner. Okay, so now I'm going to keep going. I don't really like the fact that there are these negative values here, so I know if I square everything, I can get rid of those. So in this next column, I'm going to write x minus the mean squared. So -7 squared is 49. 0 squared is 0, and you go ahead and keep computing these values out. All right, so now I've squared all of these. Well, so far I don't have much information because I still don't know about how spread out all the data is. I just know the square of the distances of all this data from the mean. So let's combine all of these values, and I'm going to do that by adding them up. So I want the sum of each value minus the mean squared. So take a moment and add these up. That is, add up 49, 0, 9, 81, and 25. Okay, and we end up with 164. So this is helpful. This is helpful since now I can come up with a measure of about how far away each value is. So to finish this computation, I'm going to divide this entire sum. I'm going to divide it by the number of values we have in our data. And in this case, n equals 5. We have 5 values. And what does that equal? Well, this is 164 divided by 5. And that's 32.8. We have one other issue to deal with. We kind of squared everything, and that made everything very large. So let's take the square root of all of this. So let's take the square root of this sum. So that is, we want the square root of 164 divided by 5. And actually, let's just write that as a decimal. So the square root of 32.8. And I get about 5.73. On your calculator, you should have computed more digits. So what have you just computed? You've computed the standard deviation for this set of data. And in fact, if we square this value, we end up right back here. This is called the variance. And this here is called the standard deviation. Now, don't mind me, I'm going to move some things around on my screen here. So using this value, 5.73, we know that on average, values deviate from the center, that is from the mean, about this much. Now, as we'll learn, that doesn't mean all the values are exactly this far away from the center, and it should be clear from this computation that it's not exact. But this will help us determine where most data should lie if it follows a particular distribution. Now, before I end this video, I want to mention some other symbols, another way to compute this. So what you have here, that is, when you see mu and sigma used, this is meant for a population. And now if you were going to compute this for a sample, the formula is nearly identical with just a couple minor changes. We use the lowercase s instead of sigma, and we still take the square root of each value minus the mean, but the sample mean is denoted with x bar, so the letter x with a bar on top. And now we actually take all the number of elements in our sample and we subtract 1. This technique is meant to make the values you compute match reality a bit more. So what I mean is when you have a sample, there's usually less spread or less variation in your sample. And a good way to think about this is if you sampled people on your campus, you are all probably a lot more similar to each other than if you sampled, say, college students across the country. So the population of college students has more variation in it. So how do these numbers help? Well, if we make the denominator here, so in this case, this one would be 5. If we were computing this as a sample, we would have 4 here instead of the 5. So what you've done is you've made the denominator of this fraction smaller. That makes this entire number larger to approximate what a population would look like.